Yeah, so I haven't done any spin-caloritronic problem ever, actually. But I think it'd be interesting for you guys to hear this talk because it's actually, these spin-over torques is right on the edge of this thermal effects, and I'll show you in the talk what I mean by that case. But the title of my talk is called Bulk Spin-over Torques at Finite Temperature and Bulk Half Hoistlers from First Principles. Before I begin, of course, I have to turn this on, and then I can go to the next slide. I want to thank the people from, there's a large collaboration with ULIC, also with Cambridge. Würzburg is where they grow the samples, and also with Prague. And so the collaboration was also here at Mainz, where we did some theory, and also in ULIC and Prague they did theory, and we compared the two, and I will show you the comparison of this material, these two theories. Also thank the funding, of course, the SpinCaT, and thanks very much for allowing me to speak here in front of you guys. SPICE, which has funded a lot of the workshop, and also the Inspire group, and also the Spin Plus X program, which is a collaboration between Mainz and Kaiserslautern. So to continue, you saw the cat in the beginning. You're probably wondering why a cat in my photo. And I think physicists have this very weird problem with cats, like we keep wanting to hurt them or something. But the idea is that when a cat falls, you know, before it hits the ground, it actually lands on its feet. And it's if you drop it from not too high of a height, but the tail will start spinning and the body will turn the other way, and it conserves angular momentum. And so the idea is we want to do this with a bulk magnet, and this is by applying an electric field. If it doesn't have any inversion symmetry, it breaks inversion symmetry, and it has spin-over coupling, then this magnet will flip itself, just like a cat does. So this is the whole idea of my talk, but before I do this, I want to give you an outline. And so in the beginning, I will bring you up to speed on what spin-over torques are and how they came about. But before that, I will actually start with linear response, and so how my view of the world and how I attempt or attack problems. And then I will discuss spin-over torques from the beginning. And then in the end, I will very quickly go over the results I have and show you. And then I will do kind of a crash landing, because the last slide I will show is some band structures of the material. And I usually don't like showing band structures, but in this case, I think this is like the first time in my life where I can actually look at a band structure and go, hey, that makes sense. Usually it's like, okay, there's a well point there, but what does that mean? So I will show you this at the end, and hopefully you guys enjoyed the talk. So to begin, we start with linear response. And so this is, you know, if you have some electric field and in a magnetic system, then you get a charge response, a transverse charge current. And this is the Anomalous Hall effect, which you guys all know, I think. And then you can do the same thing with a temperature gradient, of course, and you get the anomalous Nernst effect. And you can continue doing this, just playing around with these parameters, right? And so you can go with the spin, and you get a spin Hall effect. If you apply electric field, you get a spin response. And then you do the same thing with temperature, and you get the spin Nernst effect. But this isn't the whole picture right here. And I'm going to show you a little bit more of the picture, which still is not the whole picture, but I will show you mostly of everything that is known. So if you continue with this, we started with the anomalous Hall effect. I like this better. So we started with the anomalous Hall effect, and of course you also have diagonal conductivity, and then you have the anomalous Nernst effect, and then you have this very beautiful thing called Onsager's relation. So anytime you do one of these things, you can flip it and get another effect. So then you go over and you get effects like in the spin Hall effect, you get the Edelstein effect, or inverse spin Hall effect. You get the inverse spin Nernst effect, you get the spin Nernst effect. And then here is where the spin-over torque comes in. So you apply some electric field, and you get a torque out of it. And on the other side is what's called the inverse spin-over torque, but not many people have studied that yet. And there's only 2 papers that I know so far that has done thermal spin-over torques. I don't think there's been any experiments yet. But then there's things here, and there can be more things. And there's also this Gilbert dampening, which is a torque-torque response. But still, we have not got into how I like to view things yet. And everything here is still good, but I like to think of everything in terms of what's called a Berry's phase. And so this Berry's phase theory of everything also works in this same type of picture, where if you're in a skyrmion system, and you have 2 real space operators, then you would get a effective magnetic field, and this effective magnetic field is caused by this Berry's phase, and what happens is you get a topological Hall effect in this case. And then you can go to the other side and say, I'm only in K space, you know, and I have 2 velocity operators, and in that case I get the anomalous Hall effect. And then on these two other ends, also this is only for one band in this case, so this model only works for one band, so don't try and use it for other ones, but you get the DMI with the Gauss-Sensi-Mori interaction. This causes spin spirals in your ground state, and you also have spin-orbit torques. And this DMI and spin-orbit torques are very, very closely related. So in the sense of the DMI, it is caused in a finite system as the asymmetry of a torque operator, the moments of the torque operator in this case. And so we looked at the Gayles-Sensi-Mori interaction, anomalous Hall effect, and topological Hall effect, and iron germanium and manganese germanium, which have pseudo-skyrmions, and we published it in PRL, which you can check, and it agreed very nicely with the experiment shown here, where at this concentration of 0.8, the Gayles-Sensi-Mori interaction goes to 0, and we also looked at these things in terms of the anomalous Hall effect and topological Hall effect. And I talk about this mainly because the way we attack this problem is the way I like to attack problems, in the sense that you look at it from many different angles. You know, you don't just take, hey, I just want to look at the DMI, but you want to say, hey, I want to look at the anomalous Hall effect, the topological Hall effect, and how are all these things playing in the system. So to continue, now we go to the spin-orbit torques, and this is the paper I was telling you about, which talks about these transverse thermal spin-orbit torques. So in this case, you have just a normal spin-orbit torque in a tungsten manganese bilayer system, and then if you start to excite the magnetization, you get a current out at the end. This is an AC current, of course. And then in the other case, if you apply a temperature gradient, you get also a torque on your magnetization. And the other thing you can also do is excite it and get some heat current that goes across. But to talk about these spin-orbit torques, this language is actually very complicated, I think, because in most cases, there's two types of spin-orbit torques in this case. So what I like to call odd and even, and what most people like to call, inverse spin galvanic effect or the Edelstein effect, and the other case is spin Hall effect. And let's start with the spin Hall effect, because this one's a little simpler to explain, I think. It's when in the case when you have a bilayer system is where this language has come from, and you actually break inversion symmetry, so you have something like platinum, and then you put a magnetic layer on top, and you send a charge current through this, you create some spin Hall effect. And then this spin Hall effect will cause a torque on the magnetic monolayer. And this spin Hall effect, was discovered a while ago and by my advisor and some other people. On the other end is when you actually create this interface, you actually break inversion symmetry. And this will cause a non-equilibrium spin polarization at this interface. And this can also cause a torque on the system. And so, but the thing is that they have two different types of symmetries. And so one is usually always odd and the other one's always even in the magnetization. So there have been a lot of theories and experiments on this from the last, I think, almost 10 years or so. So you have one showing the spin Hall effect side and one showing the Edelstein effect or the inverse spin galvanic effect. And also there's been a lot of calculations on this, but up till now, up until the last, say 4 or 5 years, there has not been anything talking about bulk spin-orbit torques. And so this is what I will get into next. So the first one was in 2014 and 2009. It was first shown as possible in 2009, but they didn't call it a spin-orbit torque. So, but what they showed in gallium manganese arsenide is that in a bulk material, which becomes magnetic once you start doping it with manganese, you can have the spin-orbit torque, which is inversion asymmetric and it has spin-orbit coupling. And depending on how you grow the system, you can have some kind of shear strain on it. And what happens is this Edelstein effect I was talking about, it either has a ROSPA-like symmetry, or if you do some growth strain where the lattice C is bigger than A and B, then you get some Dresselhaus symmetry. And these are the two symmetries here. I don't know if you guys know these symmetries, like this ROSPA symmetry and this Dresselhaus. And this is very easy to see by applying different current directions, then your field will point in a certain direction. To continue, the next thing that came was these antiferromagnetic, these bulk spin-orbit torques and antiferromagnetics. And I don't think anyone ever went to the interface case for antiferromagnetics, but it went directly to the bulk. And what they saw was in manganese 2 gold, which is a very interesting system because globally it does not break inversion symmetry. but locally on each antiferromagnetic atom it does. And so then you get spin-over torques on both atoms, but they point in different directions, depending on the type of the symmetry you have. And then recently, this year, 2016, was a science paper published on copper manganese arsenide. And this is, what this result shows is the AMR of switching. So they switch this copper manganese antimony, and then they do an AMR calculation. And this is at room temperature. They're actually able to show this switching. So this is actually what they have done is they put one of these into a little USB device and shown that you can store 1 bit of information. So this is within a year and a half, they were able to do this. Is very, very, very interesting. So then what we have done actually was in this nickel manganese antimony, which is a half Heusler, we showed in our recent Nature paper the spin-over torques in nickel manganese antimony, which is this bulk ferromagnetic. I'm going to explain more. But what we did was we compared the scattering non-equilibrium Green's function approach, which I will show later down, and this Kubel approach, and they agreed very well with the experiments, showing that it has this Dresselhaus symmetry when you have this end-plane growth strain. So let's just talk about the half Heuslers first. So I told you the first material for the spin-over torque was this gallium manganese arsenide. And so in this case, gallium manganese arsenide used to be this really, really cool material because it could be a semiconductor, it's magnetic, it's metal, but the problem was gallium manganese arsenide is quite hard to do, I would say, in the first principles level. Doesn't have a very high TC, so we wanted something with a high TC, like that was bulk ferromagnetic, and the bulk is ferromagnetic. And so the first thing we came to was nickel manganese antimony, which is crystalline equivalent of gallium manganese arsenide. It breaks inversion symmetry. It's actually a half metal, so it only takes 1 spin. And so this is very nice. And we said, okay, well, I said, okay, I want to look at other things too, like antiferromagnetics, because everyone's looking at antiferromagnetics. So on the other side, you have copper manganese antimony. And the difference between ferromagnetics and antiferromagnetics is, on the ferromagnetic side, you have a spin order with M, and this is all what Helen said earlier, and antiferromagnetics don't have a spin order. And also, with ferromagnetics, they're very easily manipulated by external magnetic fields, where antiferromagnetics are not. But the good thing about antiferromagnetics is that they're very insensitive to external fields. They lead to ultra-fast dynamics, and there's many room temperature semiconductors, not superconductors, sorry. So in this sense, this is where we started. We started with nickel manganese antimony and copper manganese antimony, which I don't show any results of copper manganese antimony, mainly because the spin-over torques in copper manganese antimony won't be as efficient as they are in manganese 2 gold because they have a different type of symmetry. But now we can talk about the symmetry of this half Heusler, which you also saw from Ajaya. So here on the left is silicon, and what you have between, or it's not silicon, this is silicon in the diamond phase, I'm sorry. But you have 2 silicon atoms, and what you have here is an inversion center. And what happens is the spin polarization when you run a current points in opposite directions. But for silicon, it doesn't really do anything, it doesn't matter, it doesn't mean anything. And then you can go to gallium manganese arsenide, and the same thing happens, gallium arsenide. And then if you go to nickel manganese antimony, you have the same exact thing because you have 3 FCC lattices that interpenetrate, but you have this empty space in between that causes a inversion symmetry. And so depending on how you strain your system, you can get Rossby or Dresselhaus. And this is just a picture of what the nickel manganese antimony, when it's strained, you have some current along the 110, and your magnetization in the arbitrary direction, you have some field-like torque or odd, and then you also have some anti-damping torque, which is even, or the opposite way around, sorry, Dresselhaus. But so the strain is what we do if you take C, make it longer or shorter, and A and B stay equal. What happens is, okay, you get these symmetries. I don't want to go too much into what these symmetries look like, but this is most of the information that I plot is based on these symmetries. So how we do this in the scattering approach is we have so this is this cubic nickel manganese antimony we had. We start with setting up the system in the 110 direction where you have a source and a drain, and in the middle you have some scattering region. The scattering region we can make as big as we want. We just put many, many unit cells and they go up to 30, 40 nanometers in this case. And then what we do from the scattering regions, to simulate the effective temperature, we add some disorder into this. And so what we do is we take the atoms from their perfect crystalline sites and then we just move them off these sites. And we do many averages of this to calculate the effects on it. So we calculate the effect for one average, and then we do it for another configurational average, and do it again and again and again, and we average the effects in the end. And we do this all in this Landau-Bodecker method. So the results, what you see is in nickel-manganese antimony, this is as a function of strain. This is this black one. This is odd torque, which is this anti-damping, and then these two blue ones are the two first-order tensors, or second-order tensors of the even torque. And this black curve is actually the first order. So what happens is at 0, you have just cubic responses, and then as you start to strain it, you get these first-order effects in spin-over coupling. And it's very similar to DMI too. As soon as you start to strain with the DMI, you get first-order effects that come out very quickly. Whereas compared to things like the anomalous Hall effect, if you strain it, it may change a little bit, the symmetry will change, but the value won't change by orders of magnitude like it does here. And we also plot this in platinum manganese antimony, which is also a half metallic material. But as we do this, we also calculate things like the conductivity and the resistivity to compare with experiment to make sure everything's going correctly. And we also calculate things like the Gilbert damping, because I told you, I mean, once you can do one or two of these operations, so if you can do the torque operator, then you can do two torque operators and get the Gilbert damping. And you do a charge response, it makes it very simple to continue with these things. And then, okay, I told you we can plot these things as a function of temperature. As for instance, I showed this in platinum manganese antimony, where you have the two different symmetries of the torques in the black and green, and then the shaded region is just the, it's the amount of, what is this called? Error bars. Sorry, it's the error bars in our calculation. And the blue line actually does have error bars, but they're very, very small. So the resistivity gets very good at the mini averaging configurations. And then if you see it, if you look, I mean, in this approach, we're in this linear T regime, which is this phonon type of resistivity. And as you see, right around about 50 Kelvin, we start to screw up, right? And this is right in the resistivity. And then if you look at this torque, right around 50 Kelvin, we start to deviate also from this 1/gamma dependence that it should have. And the reason for that is the equations for these two are very similar, and in the case that for the resistivity, you're always on one band in this case, right? And then for this odd torque, it's always on one band also. Whereas this green one is this intraband contribution. This is more like the anomalous Hall effect in this case. And it does have some dependence on temperature, but it's not as strong as this 1/gamma dependence. But so then I said, okay, I need to understand more. I don't understand everything about this system. We didn't understand everything. So what we did is we just changed the Fermi energy in our system and looked at the spin-over torques as a function of the Fermi energy. And so at 0 is what I showed you for nickel manganese antimony, and 0 is what I showed you for platinum manganese antimony. And I told you that they're half metals. So in the spin up channel, it's the density of states, and in the spin down channel, it's these density states that go 0 in both cases. But if you notice, in both cases, as you just go a little bit off the Fermi energy, it peaks the spin over torques, and that's, okay, wow, that's good. You get a large spin over torque, then that's what you want, right? And so we said, how can we do this? And so what we did is we just went to the periodic table and we said, okay, hey, if you switch platinum and iridium, then you change the amount of electrons. Switch nickel with cobalt. You can also do things like switch antimony with tin, or is it 10? Yeah, I think it's not 10. It's 10, sorry. And so then what we did is I plotted these. And so the table and the graphs are the same thing. And it's exactly what we expected. So as you go from nickel manganese antimony to platinum manganese antimony, the torques get larger. But that's because of the spin orbit coupling. And then as you go to iridium manganese antimony, these torques get very, very large, almost 2 orders of magnitude larger than nickel manganese antimony. And in some cases, you can get very large anti-damping torques. So now we have a way to actually know how to manipulate these spin-over torques in these systems by changing the atom type, changing the strain. You can have just a spin-over torque that is even, just a spin-over torque that is odd, and study these things experimentally very easily. And the very interesting thing I thought here was usually, coming from the spin Hall effect and with Hyro, is that usually platinum is always the largest spin orbit effect. And in this case, iridium is a lot larger. And this is where I come to this band structure that I was going to tell you guys about. And so now I plot the two band structures, the platinum manganese antimony and iridium manganese antimony. And so in the beginning, I told you that platinum manganese antimony is half metallic. So here you have some bands that cross the Fermi energy, and they're quite linear, and you only have one spin channel in that case. And you have some spin-over torque, but it's not very large. But now if you go over to iridium manganese antimony, it's no longer half metallic, but you have bands that cross the Fermi energy, you have some flat bands here that give some contribution, you have some crossings here, and from these two I think you can see very clearly, just by looking at these two, which one should have the larger spin-over torque. And that is the end of my talk. This is the summary. I was telling you about the spin-over torque. I think the next big interesting thing for the spin-over torques would be these thermal spin-over torques in half metallic materials. But there has not been a lot of research on this yet, I think, from my understanding. And I leave with you this, a very good book of mine, or a book that I like, by Frank Hermers-Dunne, and The SPICE Expands Consciousness. I don't know if you read it, but very good book. The movie's horrible. And that's it. Do you guys have any questions?